It's a pleasure still being here now with the third presentation in a row. I hope you can see my slide and hear me. This time, I would like to talk about control system cybersecurity and why control system cybersecurity sucks. This is very deep to my heart because this is where I originated from. I'm a physicist by education. I'm working for CERN now more than 20 years. And when I came to CERN, I was developing control systems. More precise, I was developing protection systems for our big particle physics experiments. And while I was doing this, I was calculating the mean time between failures. And as you have a protection or safety system, of course, you can do. But those controllers we were using from Siemens at the time, they had an Ethernet port. And with Ethernet port, the question arose, how can I protect my PLCs against any kind of viruses and worms? This was 2002, 2003. You might recall Blaster, Slammer, the very first viruses which crept from Windows computer to Windows computer. And there we get a little bit lost. So I started in 2004. And the funny, I started in 2004 with Canada, with the British Columbia Institute of Technology, discussing cybersecurity. And over the time, I moved more to computer security, but control system cybersecurity is still at my heart. And this presentation will be more something like half around, because since 20 years, I'm frustrated because I'm still discussing the same problems with control system cybersecurity. Just to give you a little bit an idea where we're using control systems, this is the particle accelerator complex at CERN. It looks a little bit like a plan of the metro of New York or any other big city. We're starting here at the very bottom with the so-called linear accelerator 3 and the linear accelerator 4, where the particles are produced. For those who joined me on Monday, they might even have some other pictures in mind. We accelerate the protons, we're getting into the booster. The booster is then getting all the particles to something like 90% of speed of light, getting them to the PS, proton synchrotron, 99% of speed of light, then in the SPS, and later on in the Large Hadron Collider, where we can do the most powerful collisions on this planet. So that is more or less where we have industrial systems. There are lots of industrial systems. Also on the receiving side, when we collide the particles, we're taking pictures. You can think of the pictures like a digital camera. So we get collision points, 4 collision points with Large Hadron Collider, and we got zillions of different control systems there because the detectors are quite large. We're having collisions in the so-called north area and the east area where we have experiments, and they need control systems. We have radiation experiments where we do experiment with gamma rays or very hard synchrotron radiation, even harder than the X-rays which you got. We got antiprotons. We can produce antimatter in small quantities, and we can analyze the antimatter, whether the antimatter is reacting as normal matter is. And there we got, again, experiments, something like a dozen experiments, which are taking the antimatter for the physics analysis. We got isotope facilities where we're producing isotopes, which we analyze. And we got also a neutron facility where we can do the analysis. So there are lots and lots of control systems around. If you look once more, every accelerator here, which we're running a series of accelerators, needs to have control systems. So the abbreviations here stand for control systems, lots of control systems. Some of the control systems just consist out of a few PLCs, a couple of sensors. There are control systems which are much bigger, having some like hundreds of programmable logic controllers. And from those hundreds of programmable logic controllers, you get thousands of inputs and thousands of actuators. So in products, we're running Siemens, we're running Honeywell, we're running Hirschmann, we're running Schneider. We get a full cacophony of systems which are also developed by CERN and by CERN collaborators. So again, we get beam loss monitors, beam position monitors. We got so-called beam television. We got radio frequency, low-level radio frequency, but also high-level radio frequency, the beam dump, and so on. Vacuum systems. We got trench protection systems. On the experiments, we got a couple of dozens of experiments, and each of the experiments need again a control system to monitor the status, protect the system, taking the data. And we got even safety systems, starting with simple things like normal CCTVs, but also systems for detecting gas leaks, which we got here, fire or incident, how the French are doing incendie, fire detection. We got sniffers for oxygen deficiency. Here we got detectors for radiation, for the radio protection service, for example. And then we got systems for cooling, ventilation, electricity distribution, facility management, and so on. So there's zillions of different control systems. Some of them are developed in-house, and many of them are just bought from the outside. And here's some examples. This is a gas distribution system, which we got. Of course, it's connected to some kind of a internal network based on TCP/IP. This is the picture of the tunnel, which I've shown already on Monday. We could see the tunnel, which is going 27 kilometers down the line. You can see here the main beam pipe where the proton beam of the Large Hadron Collider is in, and you see an accelerated beam pipe here, because this is a so-called beam dump, where we can get rid of the beam in case we have to de-store it and dump it in a facility. This is one of the cryogenic plants with lots and lots of valves and lots and lots of sensors, just to make sure that the whole assembly of the accelerator is kept down to minus 270 degrees Celsius. This is a safety system. All the racks which are marked in orange, consisting of PLCs. In this setup here, we got something like 20 PLCs and a couple of thousands of inputs, monitoring just the experiment, whether the temperature is right, whether the radiation levels are low, whether the vacuum is correct, whether pressure is right, and so on. And this is one of the islands in our control room. You can see the SCADA system. There are some displays at the very rear on the wall, giving you the overview. And then you get lots and lots of different screens based on Linux, Windows, or on Windows, Microsoft Windows, which display the status of the accelerator, and then you can change temperatures, change trajectories, and interact with the control system. So this is more or less the setup of CERN in terms of control systems. And if you now look at the attacker side, CERN is a target like everybody else. So we have had cases in the past in the media where journalists are claiming that hackers were defacing a website of the Large Hadron Collider and came even close to turning off the particle detector. Of course, this is not true. They were far, far away, but the journalists, sometimes they have their own narrative and they don't see the full picture because they're maybe not techy enough. And here they claim that the hackers were attacking a good control system to switching off a particle detector, which is not true, but anyhow, this is what they've written. The same thing has been written here by another journalist. Hackers infiltrate the Large Hadron Collider system and mock IT security. There's even a video on YouTube which is more or less claiming that the CERN control center has been hacked. Once more, again, what has been hacked here was just one web page which was displaying the status of one of our detectors. It was a public web page, more or less displaying that everything is green, but you cannot interact with this at all. But we are targeted, and this is then what's coming out if you look in the media. So looking at control systems, cybersecurity, we got those hundreds of different control systems. The most important thing for me is the guaranteeing the integrity of the accelerator. If you recall my presentation of Monday, we are circulating proton beams. The energy of the proton beam is equivalent to 80 kilograms of TNT kinetic energy. If you can't make anything out of 80 kilograms of TNT, so I'm more or less 80 kilograms, okay, I'm cheating a little bit, but more or less it's 80 kilograms. The Boeing 747, when it's starting, and it's just at this rotation speed, when it's starting rotating and lifting off, this is more or less the same energy, kinetic energy of 80 kilograms of TNT. So now you're getting an idea how much power is behind 80 kilograms of TNT, but we got a particle beam which has just a diameter of 4 millimeters. So we're circulating a beam of 4 millimeters around a 27 kilometer long accelerator. And if this beam is getting out of control, it will be like a laser saber, like in Star Wars, opening up our accelerator and destroying our hardware, which is steering the beam into this tunnel. So it will not do any environmental hazards, but it will destroy our installations. And you can imagine, I have a professional and personal interest that this must not happen. So we have lots and lots of safety systems, control systems in place to monitor where the beam is. Here is the most easy one. It's called the beam interlock system. And if you toggle the red button, you remove the beam permit and you dump the beam. So that more or less meaning to the control system, the safety systems of the Large Hadron Collider, but also of all the other colliders, that beams need to be ejected now. It is something like, yeah, ejection is maybe even good word, because I was watching Top Gun Maverick recently. This is this eject when you eject your seat out of the fighter pilot, out of the fighter plane. And the same thing is happening here. You dump the beam, which means that you're getting rid of the 80 kilograms of TNT in one single spot, where we steer out the beam and we send the beam onto something like a concrete carbon target, which is then more or less heated up by the beam, absorbing the 80 kilograms of TNT without doing any damage. So we toggle the beam and you get the beam dumped. So what we made sure, and this is for control system cybersecurity, very important, it's very important for me, is we're making sure that if there's an attack against our installations, the damage is reduced. So we're trying to have risk avoidance by resilience and by robustness. If you have a cyber attack against our control system for the LHC, think once more of the 80 kilograms of TNT. We have to make, just by physical security, we have to make sure that the beam is ejected in a proper way in case something is going wrong. And things are going wrong. There might be thunderstorms, which might mean we lose electricity. If we lose electricity, we cannot control the beam. But electricity is very slow. It's pumping with 50 hertz. So it's just swinging with 50 times a second back and forth. The beam is doing 10,000 turns a second. So detecting a power outage, for example, we can detect this slowly. We detect this within one turn of the beam. One turn we detect it. The second turn we transmit the signal from the beam interlock system into the so-called beam dump, where we can get rid of the beam. The third turn is ejecting the beam out of the main tunnel into the target area, and the fourth is then the extraction of the beam. So we have made sure that there are lots and lots of safety systems. That is my advantage. We have resilience in the system, and we have made impact and criticality analysis to see what can be damaged, which control system is susceptible to a cyber attack, and which one of those control systems can create damage to our accelerators, and we eradicated all of them. In particular, we get lots and lots of safety systems. You remember the abbreviations which I was showing you before. Coming back to the beam is circulating 10,000 times around a tunnel of 27 kilometers. This is a positively charged beams of protons. There are hundreds of billions of protons in the beam. If you now make your maths, it's positively charged. The protons are all positively charged. They don't like each other, so they interact with each other. We got two counter-rotating beams which interact with each other. The beam itself is interacting with vacuum beam pipe, which is made out of copper. It's just inducing a mirror charge on the copper, so they're interacting. The beam is interacting with the so-called dipole magnets guiding the beam around the accelerator. The beam is interacting with the control systems because we're measuring the beam, and to measure the beam, there's some interaction. The beam is also interacting with the water level of the Lake Geneva. This is gravity. The whole accelerator is moving, not a lot, but it's moving because the water level of Lake Geneva is changing. And then there's the moon phases where the moon is pulling us up or down, depending where the moon is. And last but not least, there is the high-speed track train coming from Paris twice a day to Geneva. A train here in Europe is electricity train, so it's driven by electricity. Electricity means it is enveloped into a magnetic field, and this magnetic field, even if it's very, very faint, it is interacting with the fast-moving particles in the accelerator, so we have to also take control of this. Having said this, all this interaction means we get lots and lots of safety systems monitoring where the beam is. And if the beam is moving out of a safe space, it's something like a phase space of a good aperture, a phase space of a good turn where it should be in, and there might be areas where we don't want to see the beam in terms of position or speed. And when it's going to the non-good phase space, then we will immediately beam dump the beam and getting rid of the beam. And there are lots of safety systems: beam loss monitoring, beam position monitoring, monitoring of electricity, monitoring of the power, monitoring of the temperatures to get rid of the beam. So if you want to attack CERN, you want to bring down the accelerator, your task is a simple one, and one which only very few engineers at CERN understand the impact, is you need to find in all those safety systems a spot in this phase space where the beam is moving out of its safety envelope and is starting becoming dangerous, while the operators still think everything is green. If you remember the 2010 attack on Iran, on the centrifuge of the nuclear program, it's called Stuxnet. That was exactly what was done. the attackers were changing the rotational speed of the centrifuges of the uranium nuclear program, while the SCADA systems were still showing everything green to the operators. So the same must happen here. And for the CERN safety system, because all these interconnections between the different safety systems, but also the interaction of the beam with all the different components, there are very, very few engineers at CERN who understand in detail the consequences, and even fewer who even have a faint idea how they would theoretically do it. So we did lots and lots of impact and criticality analysis, and for the moment, we exclude that damage can be done by this. Having said that, of course, if you attack the Large Hadron Collider, if you would come down to that level, you can do a denial of service attack and just bring down one of the safety systems. Bringing down one of the safety systems, it's like with your car. If your brake is not working, best thing is now stopping your car and put it aside. If you see that your airbag is not working, best moment is to park your car and put it aside. And the same thing is with us. If one of the safety systems is faulty, it's indicating an error state, it will automatically trigger the beam dump. So what you will do is you denial of service us, and we just cannot inject beam, and the beam is just gone. So we have some downtime, but downtime for us is acceptable because in the end, we do not really produce things apart from the collisions, and the 5 minutes downtime we lose, we will just hang up in the end of the year. And downtime is also something which is created regularly because the Large Hadron Collider is a very complex beast in all its components, and sometimes there are components, electric boards, PCBs, which are just failing, and then you dump the beam because there's a failure, repair this. So it's just absorbed by the standard downtime procedures. Having said that, downtime due to security or due to security attacks, we haven't had. Technically, we had two, but this was not because of an attacker. This was because of the computer security team of CERN, namely me. We were running at former times Nmap scans on our controls network to see the robustness of the devices. Nmap is a small software which is probing internet, TCP, IP, and UDP, IP connected networks. Devices that are being tested, what services they're running. So we were doing an assessment on a regular basis, running or pinging every device once a month. Unfortunately, at that particular moment, we were hitting on some devices which were time critical, and the Nmap scan delayed the response of the devices by too much. So the devices were more or less lagging. They cannot follow anymore the beam. So they send the interlock, and the beam has been dumped twice. And it took us half a year to figure out that this was due to the computer security team. Unfortunately, instead of having fixed those devices and having more robust devices there, management decided that the security team is not doing any scanning anymore on the controls network, which I regret because I think this is the wrong action. And this is the first argument why control system cybersecurity sucks. I assume here many, many control system engineers. Maybe take one of your devices, not those ones in production, but take those ones which you have in your test systems and run an Nmap scan or an open bus scan against them. And if your device is starting to blink hectically, maybe you should think on how to protect them. So this is why control system cybersecurity sucks, and how we try to overcome that. Look at devices once more. We have the Internet of Things, and control systems nowadays, control system and the Internet of Things, or the Internet of Stupid Things, are more or less the same thing. Here's an example of an RS-232 converter. You can convert the transport layer, the communication on RS-232 communication lines into TCP/IP. This device does not come with any security, which means that if this device is hanging on a network which is accessible by colleagues, they might log onto this device. Actually, they don't log in the device, they just open the web page and they can start fiddling with the parameters. Here's another example. This is maybe a little bit too small, but you see the small panel. This is a panel of one of our conference room management systems. And again, there is no user protection, which means that if you hit this panel, you can start presentations, you can switch off the lights in the room, you can switch off the screen, the projector, and whatever else. And that is quite some fun if there's an important presentation going on and you switch off the light. Question here is, why is there no basic protection to web page of an Internet of Things device? Here's a printer. The printers are Internet of Things. You can hack them. We hack the printers and we just change completely the message on the screen, come back after lunch. But that is only something for fun. We can also read out the hard disk. And if you can read out the hard disk of the printer, all the documents, all the confidential documents stored on the, printed by the printer are temporarily stored on the hard disk. So now you got even a privacy breach there, which is not good. Question again, why are those printers not properly protected? We try to protect them outside, but I will come this in a second. Here's a PLC, programmable logic controller from a very, very known brand out of Europe, but more or less this applies also to products out of the US, out of Japan, and out of other countries. You can define a password, username, new password, confirm password, but I marked it here. It is defining this with HTTP access rights. HTTP is your web protocol to access web pages. It has two versions, the one which you shouldn't use anymore and the one which you should use. HTTP, everything over the wire is in plain text, which means that somebody who has access to the wire, and nowadays we have all access to the wire because it's called wireless. I can snoop the network of your wireless connection, and then I can see the HTTP connection, and I see in clear text how the password is going from your web browser into the PLC's web server. It must be HTTPS, because S is then the secure socket layer or the TLS layer on top of that, encrypting the communication so that people like me cannot spy on this. So here, this is already a big face palm, a blunder of the control system producer using HTTP because of saving some process cycles on encryption, putting the whole system at risk. And if you don't know this, you have to add additional layers on security on top of that. Here I got a security network camera. At least I got a choice. I can have the password type encrypted and unencrypted, or only encrypted or non-encrypted. What the heck? Why is this? Why even do they give me the possibility? They should encrypt it by the very first measures. I understand that CPU cycles in control systems are critical, but nowadays PLCs have a network adapter and the main CPU. The main CPU can do the processing of the controls loop, while the network adapter is taking care of the communication. And there should be some cycles for encryption because this is critical. Going further, this is one of our devices we have developed ourselves. It's a power converter. It's used to provide very stable 12 volts, 3 volts, -3 and -12 volts. You can see the connector here on the right-hand side, this dark gray blob, and you can see 3 Ethernet ports. Hooray! If we denial of service the Ethernet port for 90 seconds, we can kill the device. It will still spend 12 volts and 3 volts, but all the control over the Ethernet connection is dead. You cannot switch it on, you cannot change the power, you cannot control the power, you cannot monitor. 90 seconds denial of service, 90 seconds sending garbage into the TCP IP port, and the device more or less is uncontrollable. We've seen other devices where this is the case. And what this means is you have to reset the device. We have a couple of thousands of those ones in our tunnels. Can you think how many students I need to have them running around the whole complex and then to switch the on-off button on the rear of this chassis to reboot, to cold reboot the device, because this is the only way to restart in a proper fashion. So again, this is a design blunder which we corrected for. Here's a dosimeter, a commercial dosimeter which we are buying. We need to have dosimeters because going into the tunnels, our personal radiation doses is measured. Usually it's always 0, but just to make sure that we can prove that it's 0, we have the dosimeters. You can see in the bottom here a small gray cable entering. This is its TCP IP cable. And again, this device, if you denial of service this device for 70 seconds, 70 seconds, a little bit more than 1 minute, the device is crashing. When the device is crashing, you can access its memory via the TFTP protocol, because this stupid old protocol is unprotected. You access the core dump with TFTP, you can extract the whole memory of the device offline on your computer, you analyze the memory, which is not protected at all, and inside you find the administrator password to access the device, and all the devices are gone. Again, this is a fundamental blunder of the device, of the engineers of those devices. Here's an oscilloscope. It has a blue screen of death, because it was running the Windows operating system and we managed to crash it. Again, this is unfortunate. So we tested in the past hundreds of different devices. something like 17% of the devices, 17%, were devices which were able to crash. Some other 15% of the devices were failing in one state or the other. For example, we were able to denial of service the web server which was running, or if it was running telnet, we were able to make the telnet unresponsive. So the control system was maybe still running its process, but all the control to the outside world was dead. So add this together, we have something like 1/3 of the devices we tested out of hundreds of different brands and versions were able to crash. We repeated this recently with even more devices. We tested something like a couple of 900 of different devices. And our PhD student who ran this deduced that we had 13% of devices which were easily vulnerable with very easy things. You can more or less infiltrate them and you own the device. We had 2% of devices with medium vulnerable, and we get 11 devices which were configured in the way that you still can extract information you should not be able to extract. So only 3/4 of the devices were comparatively secure devices. This is what you buy today from the market. So how can I create an incentive towards the market, towards the vendor, that I would like to have more secure devices? I've spoken to many of them and they just say there is no market demand, or they say you have to protect our devices by external means. What the hell? This is the Internet of Things. Those devices might be connected at home. It is called defense in depth. We need to have the protection of the devices on the device level. And then as a security officer, I can decide to add more layers of security. And I'm adding more security layers on top of this to have ultimate protection. But the devices themselves must be robust enough and secured enough. Unfortunately, this is not what is the case. So we can make the manufacturers liable, but this is not happening. There are two products on this planet, and I see already I'm ranting too much, but there are two products on this market where the liability is with the end consumer. We're talking about software. If you buy software, if you buy Internet of Things devices, it's your liability to patch the system to keep it secure. You cannot go to Microsoft or to Apple or to Schneider, Hirschmann, all the others and say, look here, it's not secure. Please pay my money back, or please correct this or I will draw you in front of the courts. Software is something, it's a product where you take the liability, and I as a security officer have to pay for this because the engineers on the side of those systems are not applying due diligence. So that is one of the products on the worldwide market which is not subject to liability. Can you imagine what the second product is? Somebody in the chat? Nope. I tell you, drugs. If you buy cocaine from your favorite dealer, and I'm not telling you should do, but if you do, he will not give you any guarantee. You consume, if it's not working, you're bad, your money is lost. You cannot go back to him and just complain. I think this is, and tobacco, there you go. Yes, drugs in its big manner. So is there something wrong? I think there's something wrong. So my question more or less then is, what about legal requirements for bug bounty programs? There are companies, more and more companies, which providing bug bounty program. Google does, Apple does, CERN does in a certain aspect, where we are paying money to hackers which find vulnerabilities. But this is at the moment not a legal requirement. I'm still hoping that it's becoming a legal requirement, so that companies who are producing software and hardware need to pay to the first reporter of a vulnerability. So now the company can choose whether they're paying hackers which have found something, or they can invest the money more proactively in better securing their software, testing their software, and getting better products which are more secured. There is, from the Department of Homeland Security in the US, the so-called cybersecurity procurement language of the Idaho lab, which is a start, but very difficult to apply. We tried this, and the companies which were then on the bid for a multi-million project, they were saying, we can't fulfill this. And in the end, I ended up with the point to say, look here, we can't buy anything because not fulfilling this, this procurement language. So we decided to take the rules out again, because not buying anything is also not the solution. And then the Europeans started to have something like a cybersecurity certification framework for Internet of Things devices. We still have to see how this develops. I still believe certification is good, programming, procurement language is good, but in the end, we have to get the people by the balls, and the companies need to pay, and money is the only language they understand. So here are more control system devices, frequency generator. Here we got the RS-232 device, we got the oscilloscope, and now is the next question: how do I patch those devices? If you're running control system, you know already how cumbersome and how difficult it is to keep them up to date. But for some of those devices, I'm even not getting the patches because the producers are not really patching those devices. If I find a vulnerability, they just say, yeah, external protection, but you don't get a new firmware. And at CERN, what we observed the last couple of years already, now we get more and more control systems which are based on Raspberry Pis, on Arduinos, even some like system on the chips, like Xilinxes, Alteras, and so on, which you also need to keep up to date. We are able now, our SCADA systems, we are able to keep our SCADA systems more or less up to date and patch them on a higher frequency cycle. Think of older control systems. If you're getting sweaty and nervous to apply the patch, you might be able to do this once a year. This is much too slow. So how can we move from fixing bugs annually to something which is going more promptly? I can do this with a computer center, which is a 24/7 computer center running web services, which we just cannot shut down. We're running computer centers with compute nodes, which need to do calculation, which I cannot shut down. But still, we got needs in place by redundancy, by hot switch swap over, that we can still apply the patches. Maybe we should think more how we can do this control system. Just getting you some ideas how this can be done. I think this is a larger discussion. And then I'm talking to vendors, and some vendors saying, look here, we got a security solution for you. You don't use our network connector here, our network device here, but we got the secure network device here, which is even allowing for VPN functionality. You have to plug it on top of this, so you have to pay extra for security. What the hell? Why do you need to pay extra for security while I get functionality, usability, availability, all this together, and I have to pay extra for security? This should be incorporated. I've never bought a car where BMW told me, yeah, here's the car, have fun riding. By the way, you would like to have an airbag and brakes and a belt, you have to pay extra. What's that? So, if you look at the prices, for me, they are fantasy prices. So I think there's still room for improvement. And then I see more and more integrated devices like the Intel NUC here, which is definitely not an IP54 device, but still used in some corners. We're seeing more and more control systems which would like to have wireless. So dealing with USB ports already is problematic, in particular of areas where you have people frequently entering and exiting. So we put epoxy in the USB port so people cannot just randomly put USB keys in, and maybe the USB keys are infected. But now more and more devices coming with wireless LAN, and the control system itself would like to use wireless LAN functionality. Not safety systems, but control systems where you can allow this for. And this is becoming a pain. There are even some control systems which come in with their built-in wireless access points. Think of the Internet of Things you're buying today. I just had a recent example. I forgot what it was, but it is more or less asking for the configuration to connect with your iPhone to the device to set up the first password. So, and this is then, of course, also entering security problems. And then we got long-range wireless access networks with very low power, and they are more or less coming unprotected. In the moment, they are more protected by the fact that the protocol is not used by the attackers. At CERN, what is important for us is inventories. So everything at CERN, what is a digital asset, is inventoried. Here you see a list of my accounts. My primary account name is Lüders. I have a test account. And since I'm security officer, I'm owning the usual accounts, admin and user, so we can avoid that somebody is doing some bad things with this accounts. So they are mine. We have a list of the web pages. So I'm owning the April Fool web page. We got another web page. We got an inventory of web pages. We got an inventory of all the devices. We got an inventory of all the firewall openings in the outer perimeter firewall, and so on. For me, it is important that we have a life cycle. So all the devices for control systems, for the field, for laptops, for offices, we know what is connected. It's all registered. I have an inventory of virtual machines. I have an inventory of databases being used. I have an inventory of accounts, of websites, of firewall openings. Why is this important for me? Because in that case, I can avoid that I have orphaned devices on our network. In my environment, it's very often that somebody's coming with a bright idea, putting something on network because he has a bright idea. I got a brilliant idea for a website. He's creating it, we put it online, and then the person is disappearing because it was a PhD student or somebody working from abroad, and the website is still there and becoming over the time unmaintained. It's like your garden. If you don't take care of your garden, then it might become something like a little of the jungle, which might be favorable for gardens. But if your IT sphere or your systems are becoming a jungle, you cannot secure it anymore. So we have also delegated responsibilities. Every device, every web page, every virtual machine, every database, every account, and so on have a name behind. It is owned by somebody, and we have an automatic life cycle. So for control systems, you might be the manager of a control system. So you are, in first instance, responsible for the control system, which is natural, it's your baby, but you're also responsible for the security. And the security team, me and my team, can help you to have the uttermost security of your system, because you're responsible, you get now an interest. We have also an automatic life cycle, so we're verifying whether the ownership of your system is still valid, and we can do tests. So the scans on the network, for example, is one way of testing. For the firewall openings, every firewall opening at CERN is probed once a month, and we'll see, is somebody watching your web page? Is nobody's interested in your website? Yeah, we just shut down the website, nobody's interested. Why do we need to keep it open? Is there no traffic? We shut it down. And last but not least, we're moving more and more to something like one-stop shop, where we're making sure that all those different services, virtual machines, databases, networking accounts, are provided by one and only one single team. I come to this in a second. If we're talking about one single team, I start with the computer security emergency response team. I have the luck that we managed to keep all the computer security for the organization in one team. So my team is doing computer security for the data centers. We're doing computer security for office computing, finance, HR, laptops, and everything what you got more or less in your offices. But we're also doing in parallel the computer security for our control systems. So we just have one central security team. We have one central patch management system, but we have different timelines. While the computers, the Windows computers in the field used by ordinary staff running office and whatever else, they are getting the Tuesday night patches played on in a very timely fashion. While a control system running Windows, those people, the owners of the control system, getting emails saying, look here, dear Stefan, your control system is due to patching. The patches are prepared. Once you get your maintenance window, once you get the shutdown period, please apply. So all the control remains with the control system expert, because he knows best when to apply patches and when he can afford to intervene with his system. Our security operations center here is digesting something like 5 terabytes of data a day. We're storing 1 petabyte of data of the whole year for instant response. And we got a mechanism in place for auto notification. So once more for you, if you're setting up a control system web page, we're scanning it. If we find a vulnerability on top of this, we know you're the owner, which means we know your email address. And with the email address, we can send you an email saying, look here, dear Stefan, your web page is not secure. This is what we found. This is how you can fix it, because it's yours and you're responsible. But if you need help, please click here and we're happy to help you. So that is the advantage for consulting and responses. We get one computer security emergency response team. If you're looking how we do development for control system, and I don't know how you do this, but do you really do development of control systems, of real control system? Maybe the hardware is still the yes, but look at the other layers. What are you using? You're using TCP/IP, which is standard IT communication. You might use SSH for logging in, and I hope you're not using FTP and Telnet. You might use Linux operating system or some embedded Linux, or even Windows, which is standard IT. We have even people at CERN where we're running more and more SCADA system in virtual machines or even in containers, which is standard IT. The way how we programming logic controllers, how we program SCADA systems nowadays is done with the same tools which we're using for programming web pages, the same programming, not the same programming languages, but the same mechanisms. So for the rollout of patches, we use WSUS for control systems, but also for the computer center. We're using Puppet for Linux systems, Linux SCADA servers, Linux control systems, but also Linux web servers. The databases, CERN has one database team. We're providing databases to our control system experts, so they don't need to worry, because in the end, this is not their turf. Why should they do databases? They should concentrate on the controls processes And then once they have the data, they need to get calibration data or they need to store data, they just connect to our databases managed by the central IT database team. The same for single sign-on, Active Directory, multi-factor authentication. We have one identity management team at CERN. You want to log in into your control system, you use your same password, maybe with multi-factor authentication, but they are taking care of the Active Directory and of LDAP. So you do not worry, don't need to worry. You don't need to worry about the networking, and you don't need to worry about the provisioning of the operating system. So then you have more time to really design, develop, test, roll out and maintain your control system, and the underlying layers are coming from the IT department. Of course, this needs lots and lots of communication, because the database cannot just be stopped and rebooted because you have to put in a new version. So there are communication mechanisms in place where we communicate with the control system experts, asking for downtime. Because they have meetings where they declare downtime because they have to replace some hardware. And if they have to replace some hardware, we just interact, and we also then do software upgrades. Same for storage, same for web servers. So same technologies, same people, same professional people doing the support. So you have synergy effects, and you reduce the cacophony. Still, I have to admit, I don't like it. There's still a couple of shadow IT around at CERN, which you still try to eradicate. There's still too many people who think they can do better. On the short run, they might do. On the long run, they will just give up because they lose the interest. But then they have orphan system in the corner, which I need to protect, and I even don't know that they're existing apart from my inventories. So there's still too many cooks. And we have now another initiative to bring even more people closer together so that IT can serve them all, as the electricity team is providing electricity to everybody, and the cooling ventilation team is providing cooling ventilation to everybody. So it's just one of the main ingredients. So you can cook your control system, but you don't need to worry about all the rest. Does it work? It does. Does it work completely seamlessly? No, and this is why I'm giving me this red cross at the bottom right corner. It's working, but we can still do much, much better. Here you see our computer center. This is one computer center. You can see the aisles with all the servers. This one here is hosting 10,000 servers. But this is the presentation I might give them on the 15th of July on the data center nightmare. Nowadays, if you look how a data center is managed, we have web servers in here, which is serving the internet. There are web servers which are serving the IT world or our constituency in the offices. We have interconnection with our private cloud. And then we are serving web servers, databases, and so on to control systems. You need to have really some magics in place to make sure that you do not have something like a security breach from one layer to the other. But I will not go into detail here. So this is a small teaser for the 15th of July. And remember, on the 13th of July, you can learn about finance. So I'm just using this as a small advertisement. If you look at the complexity, and I will go in more detail, just looking at the servers nowadays, you have IPRI, BMC for managing the hardware. You got a virtualization system, hypervisors. You got your virtual machines, you got your containers, you need to provision everything, you have a monitoring system, and then people would like to do machine learning. This is not magic anymore. If I talk to my control system expert, they want to know how to use Elasticsearch for big data analysis, how they can do machine learning to see whether there is degradation of equipment over time so they can preemptively correct and replace the hardware. People would like to run containers or even notebooks for analysis of control systems, and so on. I'm just checking a question on the chat. There is, oh, sorry. Here is a graph of our control system network talking to the data center. The colors are different types of control systems. The green is cooling ventilation. The pink, why did we choose pink anyhow? This is electricity. You got cooling, you got cryo system. You got other control systems. Every black line, if you zoom in, is a device. We're talking about a couple of thousands of devices which are talking to each other. And if you look at this, I have really struggled to pull in clear lines to have something like a network segregation in this. So people are talking about network cells, but I got a problem. I cannot really put network cells in this overall because I just don't see how do they make sense. The second point I have is how do I control the interdependencies between different systems? They depend on each other, so I need to let communication through. The control systems of the cooling ventilation needs to talk to the cryo system, and both need to talk to electricity system. Ideally, you have a tree structure, but not necessarily you have always a tree structure. You can see Here in orange, for example, it's looking like a tree structure, but it's still not tree-ish enough that I can really have network cells inside. And then there are companies outside which are starting to force us to use cloud services. Oracle would love to see us using the Oracle Cloud. Microsoft would love to see us, instead of Excel and local MS SQL databases, to use Azure and Office 365. Atlassian and Jira are moving to a business model where it's much, much less expensive if you use their service in the cloud. But those are the tools I would like to have on my operative network, my controls network. And I definitely do not want to funnel through communication from my control systems through CERN to a data center, which might not even sit on my continent. So what if we are forced to use cloud services? We are fighting this at the moment, but if you look what the truth is, it's complicated. If we're talking about programming, this is an example where things are going wrong. I don't know how you do programming, but programming is taking the advantage that lots and lots of stuff has been written already by other people. So you just take their libraries, import them, and use them. But if you have now a library via NPM, which is looking like the library you're looking for, but is using a little of different nomenclature, different words, then you might end up with a library which is malicious, like here, a typo squatted NPM library. Here you can see a detail of a package, SSH decorator, where somebody was publishing on the internet this decorator package with some backdoor. So if you happen to use this, then you have a backdoor installed on your control system. So if you import software, libraries, containers, virtual machines, do you check them by heart that there are no vulnerabilities, weaknesses, or backdoors inside? No, you don't. Nobody is doing this because we have to go through millions of lines of code. Here's another example where there was a version of a REST client being published with the malicious contents, and there was even somebody hacking into Apple and Microsoft with the green light of those ones, showing how the supply chain can be abused to compromise companies. So my question is, how do I import securely external software libraries using PyPy or NPM? There are tools for this, like Nexus, like Harbor, similar, but are we really using them? It's very hard to roll them out, because what this means is my control system experts, my programmers, but also my IT programmers are more or less stopped in their creativity. They can't go on random sites on the internet. They have now to follow a process. And for my environment, it's very hard. So how do you make sure that blunder, bugs, vulnerabilities are detected early enough? As I said, Nexus and Harbor are some moderation tool which you try to deploy, but this requires lots and lots and lots of structure and people keeping to the rules. And sometimes people don't want to keep to the rules because they would like to get something done quickly. Here's another example. Control software programming today is not different anymore to programming. So we're using the same secure development life cycles, the same secure software development life cycles. We're using the same tools. Control system software today at CERN is stored on and hosted on an inside on-premise solution of Git. We're using Jenkins for the orchestration, Jira for the ticketing. We're starting to have a software bill of material to understand all the dependencies. We're starting to roll out Nexus to scan all the code for vulnerabilities and understand where the library is coming from, and we're running static code analysis on top of that, which is a pain because we're running millions of lines of code. And of course, the control system programmers and the IT programmers need to take those alerts actively. And of course, sometimes they just don't have the time to look into those things. So there's lots and lots of effort going on, and it's even worse if you have now to integrate commercial products. If you now do programming for a PLC from a certain brand, more or less they're using proprietary programming languages. So you have to twist their APIs to make sure that the software is not stored in their proprietary solution, but you can have the software stored on Git. Because I don't want to have for each of my different control systems, for each of my different vendors, a different solution, a different commercial solution, which cannot integrate and which has to be maintained. Here you see more control systems at CERN. You see our test facility on the top left of the so-called dipole magnets. On the right top, you see this yellow tube is one of the beam loss monitors. It's a photomultiplier and crystal inside. More or less, you can see the accelerating area on the bottom left and the beam dump we discussed earlier. So fortunately, we have lots and lots of test stands where the people have more flexibility for initial development. But then we have to roll out, and we cannot afford, because the Large Hadron Collider is a one-time prototype. It's just one, and we're developing on it permanently to make it better, better, better. And we cannot afford having a second Large Hadron Collider as a test stand. So the rollout later on is expensive and impossible if we need to have independent test stands from the top to the very bottom. So at a certain moment, we can't do differently, but we have to deploy online on the real hardware. We have at the moment a cluster of 1,000 virtual machines where the initial development is done, where you can do your testing, you test your code, and then you roll out your code. But for the real hardware, for the final development, we still have to go directly to the accelerator, which is a pain, but there is at the moment no financially acceptable solution. So I don't know how you can do this. For us, it's really a pain. You can test your system in the lab, but on a certain moment, you need to have your system, your control system, interacting with the beam to see how it's working. If the controls loop need to be fine-tuned, the controls loop need to be debugged and so on. And we have just one real beam, which is the Large Hadron Collider itself. So the final development must be done on real hardware. And we put means in place so that the access from the virtual machines to the developers to the real hardware is at least controlled and constrained. Here you can see our control room. It consists out of 4 islands for 4 different functionalities. The right island with all the cameras, this is the island where the Large Hadron Collider is being controlled of. The bottom left island, you can see all the screens which are used for controlling one of our injectors, one of our pre-accelerators. And again, we need to have remote access to this one. We cannot permanently isolate our control system. Economically, it is too costly. You have to think of our experiments, but also of components of the accelerator. We are working together with worldwide community. The Canadian light source, I'm pretty sure there are experts in Canada of the Canadian light source working with experts at CERN, or with Triumph in Vancouver, or with Brookhaven close to New York, or Tevatron Fermilab Chicago. We are all working together with people at KEK in Japan, or people in Beijing, and so on. This is a community, and some components might have been developed by your folks at the Canadian light source or at Triumph, and then being shipped to CERN. But if it's failing, we cannot afford flying people in. It's taking too long and it's too expensive. So having the first glimpse on the system for debugging must be done remotely. So we need to put means in place to remotely access those islands. And this is now a question of security versus usability and cost. And there's an accepted threshold, which is making us very hard for us. So the solution for us is we're rolling out multi-factor authentication for everybody who wants to remotely access our control system, which is working very nice on the web sphere, which is working very nice on virtual machines based on Linux and on Linux operating systems alone. But if you want to roll this out on Microsoft PCs and Microsoft Server have no integrated functionality using multi-factor on premise. It's using multi-factor passing through Azure in the cloud, which is exactly what I do not want to do. So there is no silver bullet for Microsoft. The solution at the moment is we just get rid of Microsoft and we have Windows terminal servers, which are then more or less becoming Linux application gateways. Authentication is a pain as such. Here is a security camera. Sorry, I've been too fast, where you even see the default password 1234. We spoke about this one. Here you see, would you want to change the telnet config password? Hell no, this is a thermometer, but you should not run thermometer. You should not run telnet. This is a coffee machine. You can configure this. Its configuration is public, and the security team was drinking coffee for free for a while because we figured out that nobody cared to change the default passwords. So once more, when do we get the defaults right? If you're running control systems, if you buy in devices, maybe Google now for your device with the brand, with the make, with the model. And if you find out the password on the internet, I'm pretty sure you find the password with a little bit of Google hacking, and this password is the one which is working on your device, maybe time now to change it because anybody else can figure that out. So I wonder why we don't get those devices in such a way. Once you set it up, you're being asked to create a password from the very beginning. And then integrating a coffee machine like this one into Active Directory and LDAP. Okay, you might not care for a coffee machine, but for control systems, I do care. My oscilloscopes should use the same logging scheme I'm using for everybody else. I don't want to have every control system with its own user base, with its own passwords, because those passwords will just leak around all over the place, being written down and then getting lost. And if passwords getting lost, then this is the primary entry door for attackers. Last but not least, education. We are control system experts, we are not IT experts, but we're doing IT. We are setting up web pages. We should learn how to do proper programming to avoid cross-site scripting, where your browser is executing the command you type onto the command line in the URL bar, or directory transversal, where the input is not filtered. And if you look at the very top, it's saying site : /////. It's more or less going the directory tree up and then going down again to the etc password folder and displaying the contents of this file on the web page. This is bad programming. This is bad filtering of inputs, and filtering inputs, sanitizing input is the most important things programmers should do. Whenever you're accepting input from an untrusted source, make sure that you just get the input which you expect, and everything else is discarded immediately. It's not the case here. It's asking for directory transversal. This is even the worst example, where we lost one web server a long time ago in 2009 because it was not sanitizing input. So my question is, we got students in control system engineers studying control system engineering, computer engineering, IT stuff, hardware development, programming for control system, Arduinos, Xilinxes, and so on. Why do those students not come with security knowledge? I'm seeing lots and lots of students, and if I talk to them, yes, I had classes in operating systems and in databases and doing ladder programming from control systems and in C++ and setting up web servers. What about security? Yeah, security was not doing the bachelor. You can take this as a separate master course. What the hell? Why are we doing this? We got courses for integrated functionality, usability, maintainability, availability, all together because we care. And we have to put security as the black sheep as a side. That is wrong, isn't it? We need to have this together. Me giving a presentation on security is already wrong, because security should be integral part of everything else, but unfortunately it is not, and I still have to go give this presentation. I hope you take something home and you see how you can improve your control systems. In particular, if you're a manager, worry about your control system. What is happening if I hack into this one? Can I do destruction? So we're doing training. Here's some training we've done, programming training for control system experts. We're giving training on how to program securely in PHP and Perl and Python, in C++ and Java, but also how to do programming for control system using WinCCOA, for example, how to set up control systems. We've done in the past, long time ago, with an external company, serious gaming. You see here the board called KIPS. It's simulating a water purification plant. And then the game is, we had 20 groups of 4 people in a room. So we had 80 people at 20 tables, and they were playing this game in competition. Everybody got this board, everybody got a card, a deck of cards where they can play and buy a firewall or doing awareness or deploying antivirus software. And everybody has an iPad. And the iPad is showing you the money you're generating by purification of water. You're getting deduced money if you buy a firewall because it costs money. But then after the first round, the attackers come and striking. In the second round, they're trying to strike hard. And if you didn't put your defenses up, now you will lose money, but not because you bought a firewall. You will lose money because your control system is compromised and you do not have any pure water output anymore. That was fun. Lots of control systems took lots and lots of things away. Learning better why I am here, why I'm helping, and why I care. And they also started caring. So we are doing similar training for IT administrators and control system experts. We're providing a consultancy team for system architecture and the choice of components. So people come now to us very early from the control system side, but also from the IT side, say, look here, we are planning to set up a new monitoring system for radiation or a new monitoring system for our dustbins. Yes, we have a monitoring system for dustbins, actually. So this is how we plan to set it up with this external company. This is the product they provide, how we can integrate everything together to make it functional, secure, and using most IT central provisioned components, so we do not have any additional cacophony in different components like different databases and corners, orphan system and shadow IT. So this is a big success. And we even now trying and started training so-called white hats, people who are penetration testing into system. We train them how to do penetration testing, vulnerability assessments, running scans. And while they do this, they improve their system, because initially the idea was that we give you the permission to hack into the system of somebody else. So something like having a game. But it turned out that most people don't ask to hack into the system of somebody else. All of them more or less are hacking into their own system, not in production, of course, but they control the system. So if they screw up, it's their problem anyhow. But they now hack into their own system to improve computer security, come back to us and say, look here, I tried to run this tool here, I penetration tested. Is this looking really not so good? How can I fix this? So that is a very big step forward in sensibilization and awareness raising. So coming to my end, time is running fast. Why do control system cybersecurity suck? If you're looking at the threats outside, they are not going away. With the political scenery, nowadays it's even becoming worse, but it was already bad in the past. There are more threat actors, there are more skilled threat actors, there are more attackers which are interested in control system, some of them because it's fun, some of them because they're nations and they would like to infiltrate your control system because maybe in the future this might be beneficial for them. There are cyber criminals which just want to extort money through ransomware attacks and so on. The threats are increasing and not going away. If you look at your control systems, they're becoming more and more complex. More complexity, more independence, interdependency means more vulnerabilities. It's very easy. Yeah, if you have one sheet of paper with some text on, you can protect it. If you have a library full of books, it's already much, much harder to protect this. So there will be more and more vulnerabilities. And if you look at the consequences, we are living in a world which is highly interconnected. We are living in symbiosis with control system. I don't know in your place, but if the electricity is going away here in Geneva Basin for a week, then we have anarchy because the people can't get any food anymore. They can't go to the filling station because the pumps for petrol are based on electricity. You can't pay because you're paying with credit cards. You can't go to the ATM anyhow because they are on electricity and so on. So we are interdependent. Our control systems becoming interdependent, more and more complex again, which means that the consequences are becoming more and more severe. So this is why control system cybersecurity sucks. At CERN, I'm really trying to control this environment of Arduinos, of Raspberry Pis. Windows is on the way out, fortunately for control system, but it's not getting better with Raspberry Pis. On the other hand, we have a central provisioning for the patching, so there is some light at the end of the tunnel. If looking outside the core of the control system, so really the field bus layer, which is really integral of the control system, where you got Modbus or we're using Profibus or something which is really local, the interconnection between control systems are growing. They're talking nowadays, maybe even with some meteorological stations to know what the temperature outside is. So the interconnections will grow, which means that you have to protect your perimeter. We put multi-factor into the place, and we have an intrusion detection system, which is even on the control system layer, where we get the connections between the data center and the operative networks. IoT control system, I think I should have twisted this better. I think it's now the same thing. You're buying devices which are not smartphones, tablets, or computers. You're getting devices which are running an operating system, even maybe a popular operating system, completely unpatched, unsecured with vulnerabilities. And this will not go away. So we're trying to have more and more central services to counter this. If I have a central service, central database service, central web server, I have professionals which can make sure that at least that part is as secure as possible. While it's on the plant 4, this is a professional fault at CERN. We do not allow Wi-Fi on the plant floor. We have the luxury that we have lots and lots of caverns underground and tunnels, which means that the signal cannot leak out and we control the area. So a deployment of Wi-Fi is forbidden. And if somebody is still doing it, this is a professional fault. Every device which is going on the network, if it has Wi-Fi capabilities, there must be a proof that it has been disabled if you can't even remove the chip. Last but not least, internet and cloud access will become normal for us. Remote access is already, but then you need to make really sure that you have a staged hopping from the internet to the plant 4. We have different gateways for different kinds of engineers coming from Canada, logging into CERN over several hops with multi-factor authentication if they want to really go down to the control system. And for some systems which are critical, they need to even get the local authorization by the operators in charge. And then where are the incentives to have secure control system? We have no business cases. Bug bounty programs might help, but help me. Go to your vendor, complain to them, and ask them why can't they produce something which is secure. And with this, I'm done. Thank you very much. If there are questions, happy to answer.
Well, thank you very much, Dr. Lüders. This is just as informative and comprehensive as I thought it would be. So first of all, I'd like to request everybody give a round of applause here to Dr. Lüders. This is a very great presentation and very worthy of our lunch hour, I believe. On that note, I'd like to open the floor here to any questions. Again, you can enter those there into the chat, or you can unmute yourself and directly speak those. Perhaps. Okay, we have a question already here from the floor. Thank you so much for this. This has been a great series. You spoke a lot about dumping the beam safely is one of your principal concerns where safety and security intersect. How do you go about looking at other assets that can present risks in the environment, such as pressure vessels and boilers and their interaction with cybersecurity?
Good question, Ellen. That is my advantage. So I have the luck that the safety of the accelerators are of paramount interest because they can be destructive, which means that if we have pressure vessels and boilers and other systems which are critical to the operations, the safety systems already taking care of this. So the same holds. If we care about the safety of those vessels and boilers, cybersecurity is also becoming part of this, because then hacking into the system, you need to bypass the safety mechanisms. And the safety mechanisms at CERN, it's like a rocket launch. If you remember the countdown, and then you check, are all systems go? Yes, comms is go, and fuel is go, and whatever else is go. The same thing is happening for us. Before we inject the beam into the LHC, so the injection is taking something like 2 hours, injecting and accelerating, and then we are running the beams in the accelerator, if we can, for dozens of hours, between 12 and 30, even 40 hours in the machine. But all the safety systems pre-injection need to give their go, and the beam dump in particular are then more or less put on an autonomous mode. So the beam dump is pre-charged. The beam dump itself is consisting out of a bank of 14 redundant capacitors for each beam. They are huge capacitors of length of 3 meters. They're all pre-charged and they're autonomous. So whatever you do, you cannot touch them. If you touch them, the only thing they'll do is they will discharge. When they discharge, they will dump the beam. That is the purpose. If they internally malfunction, they are developed in such a way that if they malfunction, they will discharge and everything will dump. I have said they are redundant, so the first chain of 14 will discharge, and if it discharges, the other 14 will just follow something like a couple of microseconds after and discharge again. So if the beam hasn't been dumped by the first turn, it will be definitely dumped by the second turn. So we're making sure that everything what is safety critical is in this beam interlock system triggering a beam dump. So the safety systems, and I believe in this control system is running the process, but you need to have hard limits in place given by safety systems which are non-alterable, and they are less alterable even where the more important they come for your system. So a safety system for one vessel might still be connected and being remotely programmable. If you have the entirety of the whole pressure system, then the safety system is designed in such a way that no harm can be done, or the safety system will trigger and we put everything to a safe state. Having said that, lots of the installations are also industrial. So if you're talking about vessels, cryogenic systems, cooling ventilation, this is what we buy more or less out of the shelf, and then the standard safety principles and the standard safety standards like ISO standards apply for those systems. Welcome.
I have a question. You mentioned there that you had a conflict with Nmap delaying and interfering with the control systems. What did you learn from that conflict, and what would you do differently now if you were given the same sort of opportunity again?
So the learning is that our development processes need to change, because we need to take robustness at the first level of security more into account. Because in the end, the Nmap scan, if you know Nmap scans, you can run Nmap scans aggressively. But if you do an Nmap scan or do a denial of service attack against whatever, you will bring it down. So it's not a question of control system. If the control system is failing because of denial of service attack, it's just a question how it fails. But you can bring down everything. You can bring down CERN's firewall if you do a denial of service attack from the outside. You can bring down everybody else with a denial of service attack. We've seen this in the past. So what's learning is a gentle Nmap scan, which is just doing some queries a second, maybe 10 queries a minute. the devices should not be concerned by this and just ignore the noise, because now it's an Nmap scan, but our controls network is vast, and sometimes you have some devices which are failing and then starting to do oddly things because they are broken, and everything else needs to be robust against this. So we're trying to have now more robust, in particular to the systems we develop. We develop, for example, our own switches for where we have time constraints, but also we're talking to the vendors where we're doing Nmap scans, and we confront them with the result of the Nmap scan and telling them, look here, we scanned your device with Nmap, with OpenVAS, which is something like Nessus, and telling them, look here, this is what we found. This is basic 101 security. This is the school kid security you should do yourself in your company to provide your device with some certain level of robustness. But it's a chasing, and I don't have a more clever answer than this. We're chasing, we're trying to do better, but the amount of devices which come into operation, it's very hard to keep us up with them to make sure that they are robust. Having said that, just to break it, I mentioned that more and more people coming to us for IT consultancy, and those people to come to us, this is where we immediately kick in and say, look here, you got some devices, so let's make a penetration test and see what we can do. We got some lathes and 3D printers and drilling machines, which we were able to bring down. But it's just a lathe, interconnected, because you would like to have remote maintenance from the company. But again, it's just a lathe. If the lathe is going down because it's compromised and infected, you can still manipulate your metal. You might not do anything else, but has no impact on operations. It's just more produce, and you fly them the personnel in. But those lathes, those drilling machines are not in our controls network. They are put on a network aside from this, where if they go down, I can care less. They're not safety critical. They're not operation critical.
All right. You mentioned some switches that you developed in-house with timing constraints. Would that be the White Rabbit protocol?
Oh, wow. Yes, indeed. Thank you very much. This is the White Rabbit program, which is done by many, many different sites worldwide working together. It's something like an open source repository for hardware. And I would love to encourage you all, if you got PCB designs or projects which is based on hardware, why don't we make this public? Why don't we share this? We share code, but there are lots and lots of nice PCBs with high precision timing, high precision communication, measurement of voltages to a very high precision. Those boards we should, if we can, if they're not proprietary to your company, we should make them public and putting them into a repository. And the White Rabbit project is one of those. This is part of this open hardware initiative, which is done by several high energy physics sites worldwide. And I think this is the right place. Yes, there you are. These switches are part of White Rabbit.
Well, I'd like to give anyone else here a chance to ask a question or two if they have one.
Do you find that you have difficulty convincing management that the security and prevention protocols you put in place are worthwhile in terms of a maintenance window? Because I know that a lot of the sites that I work with, we want to operate 24/7. Doesn't really, security is an afterthought.
Moin, Stefan. Indeed, this is a problem. So management acknowledge that security is important, and we're doing security outside in. So we're protecting our outer perimeter, and then we're going inside. The closer you come to the control systems, the more it needs to be planned. So as you're saying, you have shutdown periods, and we have shutdown periods. We have, over Christmas, we got always a couple of weeks of shutdown, and the general patching of all systems is then part of that. I have the power to ask for emergency patching if there's something really severe coming up. Log4j might be an example, or Heartbleed in the past. So then we time this more closely to a technical stop, and then we can intervene. So there's some interconnection, but yes, there's always, of course, the balance to be found between uptime, operations, produce, and security. So I cannot come with little things and ask for a shutdown. It needs to be justified. But we have a very good collaboration. We try to have more collaboration and even more interaction to get more security in. On the other hand, also the control system experts now relying more and more on IT technologies, as I said. So it's mangled now. There's much more cross discussion, cross service, and cross provisioning, which is then helpful. But of course, running accelerators 24/7, this is the main prerogative, and we have to work and we have to live with this and put other means in place to buy us the time to keep running. So this is why we have the defense in depth paradigm, which everybody else should have. So we have other layers which are taking and keeping the evil abroad, and we can buy us some time to run the control systems in an untampered fashion. Is this answering your question?
Yes, it does. Thank you. And I guess one more follow-up question. Sorry to keep everyone. Are there any recommended courses or certifications you'd recommend for learning more about cybersecurity as it relates to control systems?
That is a good question, but I think I have to pass that question. I'm pretty sure that SANS, maybe Idaho Lab, have good courses, but I just don't know. I just don't know. Actually, that's. I might have a colleague who knows this better, who is more involved directly with the application of cybersecurity for control systems. But no, I can't. If you drop an email to Juniper, maybe I can figure that out, and we send you an email with the answer.
Yes, I'd be pleased to relay any information that other people have at a later date. Alan has indicated that he's been impressed with everyone who's met who has had their SANS GICSP. I assume that's some manner of certification.
Okay, so he's not impressed with me because I haven't. I don't have it.
Well, he doesn't say he's unimpressed with those who don't have it. He's just said he's impressed.
I'm teasing. No, I think the SANS courses are usually very good. So if they're courses for control system cybersecurity, or even general cybersecurity courses, which might apply also to you, because I assume you, in one way or the other, you're touching networks, you're touching databases, you might even touch web servers. So there are lots and lots of SANS courses which might do so. Coursera is also providing security courses. Udemy is providing security courses. Those would be my first guesses to look at. But as I said, drop us an email and I can check with my expert what he would recommend in courses.
All right. Do we have any more questions?
Nope.
No, it does not appear so. So I would like to ask everybody to give another round of applause to Dr. Stefan Lüders. And I wish to thank you all for taking your lunch hour to come to this presentation rather than eating something from the cafeteria or whatnot. But on that note, I will end this